Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So hi everyone. Alright, so in this video I will explain about Coulomb's law. Alright, so before we go to the definition of the Coulomb's law, so let's look on this figure first. Alright, so basically an electrical field is produced by a particle charge. So let's say we have a particle charge here, and the sign for this charge is a positive. So because of this case, so this charge will be induced the electric field in outward direction from its particle charge. So however, if we have a negative sign of charge, an opposite direction of electric field will be produced. So let's say we consider this is our direction of the field. So let's consider if we have one test point located at any P point, and then the vector that represents the direction and distance from this particular charge and this P point given by this vector of R. And because of that, so we have this is R cap, which is the unit vector for this distance and direction between charge and our test point. And let's say we have another charge here, so we put another charge, and the charge is in a positive signs, and this charge is in presence of electric field that produced by this particular charge. And because of this fact, so this charge will be experience certain force due to the electric field that produced by this particle charge. And because of the sign of both charge is a positive or same, having the same sign, so basically a repel force will be developed, and the direction of force will be in this direction for both particle charge. So the question is, how can we derive expression that represent our electric field here? So one method that can be used in order to derive the expression for electric field here is by using Coulomb's law. And the Coulomb's law states, first, the electric field induced by any isolated charge or particle charge can be calculated by using this expression. So whereas we have, this is vector E, which is represent our electric field intensity, is equal to R cap. So this is our unit vector for the electric field that produced by this charge, Q divided by 4 pi epsilon R squared, where this is the distance between our particle charge and the test point, like as shown in this figure. And the unit for this vector E is equal to volt divided by meter. If the case that we have another particle charge that we put in a presence of the electric field produced by this charge, so the force of that experienced by this charge can be calculated by using this formula. So whereas the vector of F, which is the force, is equal to Q, so this is the value for this charge multiplied by the electric field intensity that has been calculated by using the previous equation. And the unit for this force is equal to Newton. So however, so let's say we have more than one charge, or let's say we have two charges, and we need to calculate, so what is the value of electric field produced by both charges in this location. Because of, in this case, we have two charges, so basically we will have two different components of electric field produced on this point. So one is this E, or this field that produced by Q2, and the other one is in this direction, the electric field produced by Q1, so our first charge here. So in order to calculate the potential or the electric field produced by this point, so we need to add, or we need to add the two electric field that produced by each charge. Then we will have the electric field intensity at our test point P is equal to E1, which is the electric field produced by our Q1 plus vector of E2, which is the electric field intensity that produced by our Q2. So the distance and the direction between our Q1 to the origin point, so given by this vector R1. So the vector R is represent our distance and direction from our origin to the test point, and the vector of R2 is represent of direction and distance between our origin to our Q2. And the direction and distance between our Q2 and test point, and as well as our Q1 and our test point, given by this vector respectively. Alright. So first we need to calculate what is the expression that represent our E1 vector, which is the electric field intensity produced by our first charge here. So by referring into Coulomb's law equation, so the equation that we need to use to derive our electric field intensity that produced by any insulated charge is given by this formula. So therefore, we have this formula, and then we need to derive, or we need to replace the r cap and r squared value. So here we have the vector of E1, which is the electric field intensity produced by the Q1 is equal to r cap Q1 multiplied by Q1 divided by 4 pi epsilon r squared Q1. So the vector of RQ1 can be defined by this expression by referring into this vector that we have been derived just now. Whereas we have our RQ1 cap, so the vector between the vector that represent distance and direction between Q1 and our test point is equal to vector R minus vector R1. And based on this vector expression, so we can derive the amplitude for this vector given by this expression. So whereas the amplitude of vector of R minus vector of R1. With the concept, or by referring into the equation for the unit vector equation, so unit vector is equal to vector divided by its amplitude. So therefore, for r cap Q1, the expression that represent our r cap Q1 is equal to vector R minus vector R1 divided by its amplitude. And in order to put all these parameters inside this formula, so first we need, let's derive our r cap Q1 divided by magnitude of r Q1 the power of 2 as given in this formula. So we have r cap Q1 here, and we have r Q1 to power of 2. So this is amplitude for this vector. So by referring what the expression that we have been derived before, so we will have RQ1 cap divided by RQ1 magnitude of RQ1 the power of 2 is given by this expression. So whereas we have R cap R vector of R minus vector of R1, so divided by vector of R minus vector of R1, this is the magnitude sign, and because of, even though we have this is the power of 2, but in the fact of in the r cap formula, so we have another amplitude here, so that's why in this case, so we will have the amplitude for this on this side will be a power of 3. So when we consider all the expression, the formula that we have been derived, so we put again so whatever that we have been get just now into this formula, so we will have the expression that given or represent of our E1, or vector of E1, which is the electric field intensity produced by our Q1, is given by this expression. So whereas the vector of E1 is equal to Q1 divided by 4 pi epsilon multiplied by the vector of r minus the vector of r1, so divided by its amplitude with power of 3. Same goes to the expression of our vector of E2. So we will have the vector of E2, or the vector of electric field intensity produced by our Q2, is given by this formula. So whereas the vector of E2 is equal to Q2 divided by 4 pi epsilon multiplied by the vector of R minus the vector of R2 divided by its amplitude with power of 3. Okay, because of the electric field intensity in this point is equal to summation of both electric field intensity, then we will have the electric field intensity on the test, our P point is equal to vector of E plus vector of E2, and this is the result of the summation. So we have, this is the expression that we have been derived for our E1 vector, and this is the expression that represent of our E2 vector as we have been derived just now. And if we consider more than 2 points or up to n point of Q exists in any medium, so we will have the general expression for the electric field given by this expression. So whereas the vector of E is equal to 1 divided by 4 pi epsilon, a summation from I from 1 to n, so this is Q1, so the value of its charge, so multiply by vector of R minus vector of Ri, so this one is the vector of for each dedicated particle charge, so divided by its amplitude with the power of 3. Alright, so in order to understand this topic, so let's look on one example. Alright, so let's say we have 3 particle charge. So for example, we have Q1, the value for Q1 is equal to 5 microcoulomb. So the value of Q2 is equal to 4 microcoulomb, and the value for the Q3 is equal to 2 microcoulombs, and each charge is located on dedicated coordinates. Then we need to find the expression or the value for our electric field intensity that produced by all of these charge at the P, our test point P, the coordinate of P given by this coordinate, which is 1, 1, 2. And by assuming that all the charge is reside on the A or in a A space, so because of that, so we need to use, instead of we are using epsilon, so we need to use epsilon naught, which is the value of electric permittivity of air. So by referring the equation that we has been derived just now, so the electric field intensity, if we have consider more than 2 charges, is given by this formula. Alright, so in order to find our expression for E, so we need to calculate for this vector first. So the vector of R minus the vector of Ri divided by its amplitude to the power of 3 for every charge, particle charge exists in this problem. So let's say we have for the Q1, so the vector of R minus vector of R1 is given by this expression. So this expression is basically the coordinate of P minus the coordinate of Q1. So we will have, so 1 here is minus 4. So 1 is minus 4 plus y cap. So y cap 1 minus 3, which is this coordinate, so minus by this coordinate. And a plus z cap 2 minus 1, which is this coordinate minus by this coordinate. Then by solving this expression, then we will have the vector of that represent the distance and direction from our test point to the Q1, so given by this expression. And this is the amplitude for that vector. So we just summing all the square root of each component of x, y, z, and then we will have a square root of 12. Same goes to the Q1. So in order to find the vector that represent direction and distance between our test point and Q2, so that vector can be derived as below. So we have x cap 1 minus 3, which is the vector, the coordinate for the P point in the x component, so minus by this value of coordinate. Then we have x cap 1 minus 3, and then for the cap and for the y cap component, so 1 minus 2, which is this coordinate minus by this coordinate, so y cap and y cap component of a P point and as well as our Q2, and plus z cap 2 minus 2, which is this value of coordinate minus by this value of coordinate. Then we will have, this is the vector that represent the direction and distance between our test point and our Q2, and this is our amplitude for that particular vector. So again, same goes to our last particle charge. Alright, so we need to find the vector that represent direction and distance between our test point and our Q3. So we will have x cap 1 minus 0. So basically the coordinate, the x component for the coordinate P, so minus with the x component of the Q3. So we will have x cap 1 minus 0, and for y cap, so we have 1 minus 0, so we will have the same arrangement. So we have the y component for our test point minus with the coordinate of Q3 in the y component, so we have 1 minus 0, and for the z component, so we have 2 minus 5, so that's why in this case, so we have z cap 2 minus 5. And by solving this equation, then we will have the vector that represent the distance and direction between our test point and our Q3, and this is the amplitude for that particular vector. So once we have been derived all this vector that required, then we can put all the vector and the amplitude inside this general equation. So we have, for example, for our Q1 here, so we have Q1, so the value of the Q1 given in the problem is equal to 5 microcoulomb. So this is the vector that represent direction and distance between our Q1 and the test point. So similar like this vector that have been derived just now, and divided by amplitude the power of 3. So we have, this is amplitude the power of, with the power of 3. So plus, so this is the value for our Q2, so 4 microcoulomb. So this is our vector that represent direction and distance between our Q2 and test point, and divided by its amplitude with the power of 3. So we have, this is our vector that we have been derived just now, and this is our amplitude. Same goes to the last expression of this formula or equation. So we have 2 microcoulomb, which is represent the value for our Q3, and this is the vector represent direction and distance between our Q3 and a P, so as we have been just derived just now, and divided by its amplitude the power of 3. So by solving all this expression, then we will have the equation that represent our electric field intensity, so given by this vector, whereas minus x cap 9.18 minus y cap 4.89 minus z cap 0.397 kilovolt per meter. Alright, if we have been learned before, so the Q also can be represented by its charge distribution or its density value. So the Q can be represented by line density. So we have rho L here, and in order to find the total charge in a certain length, so we need to perform line integration of rho L dot with dl. If we have the charge in a surface density value, so we have rho S here. So in order to find the total charge in a surface, so we need to perform a surface integration rho S dot ds in order to find the total charge. And the charge also can be exist in the volume density. So we have rho v here. And in order to find the total charge enclosed in any volume, so we need to perform a volume integration of rho v dot dv. So because of that, so the value of Q here can be represented by any equation here. Okay, so for example, if we have a line density of rho L, the electric field intensity produced by this charge is given by this formula. So basically what we done is just we replace the Q here with the formula of this line integration. So therefore we will have the vector of E is equal to 1 divided by 4 pi epsilon. So line integration r cap divided by r vector power of 2 rho L dl. So this expression is like the expression that we have just now. So basically we can rearrange this formula to become like Q divided by 4 pi epsilon, so multiplied by r cap divided by r vector the power of 2. So in this case you need to know, or you need to distinguish between r cap and the vector of r. So r cap is the unit vector that represent r cap is a unit vector for the vector that represent a distance and direction between our Q and our test point. So this is the amplitude for that particular vector. So because of that, so we will have, let's say we have our charge is represented by each line density value. So we will have the vector of E is equal to 1 divided by 4 pi epsilon, line integration for r cap divided by amplitude of vector r squared rl dot dl. Same goes if we have the charge in terms of surface density of rho s. So the vector of E, or the vector of electric field intensity, so given by 1 divided by 4 pi epsilon. Surface integration of r cap, so divided by amplitude of vector r with the power of 2 rho s dot with ds. And if we have the charge is represented by its volume density rho v, so the electric field intensity can be calculated by using this expression, whereas vector of E is equal to 1 divided by 4 pi epsilon, volume integration for r cap divided by amplitude for vector r squared rho v dot dv. Alright, so let's look another example, so that represent the how to calculate the vector of, or the value for the electric field intensity, so due to the charge distribution, or due to the density value of charge. Alright, so let's consider we have one line charge, or line charge density reside on the z-axis here, and the rho L is given by 8 microcoulomb per meter, and the length for the line charge is from 0 until 0.05. So this particular line charge is reside on the air, so we need to use the epsilon naught, so rather than epsilon. And the vector that represent the distance and direction from this line to our test point is given by this vector, and our test point is given by this point. So whereas the test point is equal to 0, 0.1 and 0. So let's derive the expression for our electric field intensity, so produced by this line charge density. Alright, so in order to find the electric field intensity, so produced by this line density, so this line charge density, so we need to use this expression. So whereas the vector of E is equal to 1 divided by 4 pi epsilon naught, so now we are using epsilon naught rather than epsilon, because in this question the line charge is reside on air. So line integration of r cap divided by magnitude of vector of r with the power of 2, so rho L dl. So based on the information that has been given in this question, so we will have the value for rho L is equal to 8 microcoulomb per meter. So dl can be replaced with the dz since this line charge density is reside on our z-axis here, and the limit for the z is from 0 until 0.05 meter. So as given in this figure. Alright, so first we need to derive this vector. Okay, so the vector that represent the direction and distance between our line and our test point here. So similar like what we have been derived just now. So the vector of r is equal to x cap. So 0 minus 0. So this one is because of, in this particular case, on this line, so we have a coordinate of 0, 0, z. Okay, so we cannot put any value in this z because the z could be any point along this line. So the line from 0 until 0.5. So instead of, we are replacing this value of z with some numerical value. So we leave this coordinate as z only. So first we have the component for x cap is 0 for both vector. So either, for both coordinate, so either for the test point and our line charge density. So 0 minus 0. So plus y cap 0.1 minus 0. So because of, on our test point, the coordinate on the y component is equal to 0.1, and for our line charge, the value for the y cap is equal to 0. So that's why we have 0.1 minus 0. And for z cap, so we have 0 minus z. So in this case, on our test point, the value for the z component is equal to 0, but for our line charge, the z component is equal to z, and the z value is either is in between 0 until 0.5. So we will have our expression that represent the r vector is equal to y cap 0.1 minus z cap z. So the amplitude for this vector can be calculated by using this formula. So the vector for r is equal to square root of 0.1 squared plus z squared. The r vector can be calculated by using this formula. So the vector of r, so divided by its amplitude, then we will have this expression, which is represent our r cap value or r cap expression. So with the expression that we have been derived just now, especially for the r vector, so we can put all the formula that we have been derived inside this formula. Then we will have, so the vector of E is equal to 1 divided by 4 pi epsilon naught. Line summation, so summation from z is equal to 0 until 0.05. So this is our r cap. So whereas our r cap is equal to the vector of r divided by its amplitude, so we have this expression. So this is our r squared, r amplitude of r squared. So we will have 1 divided by square root of 0.1 squared plus 0 plus z squared and the power of 2. So this is the power of 2 here, multiplied by rho L. So the value of rho L given in this question is 8 micro. So we have 8 micro here, and dl has been replaced with the dz. So by solving this expression, then we will have, this is our final expression before we can perform the integration process. And by solving this integration, so we will have this expression. Then if we put all the limits value inside this expression, so we will have the electric field intensity formula, or the expression that represent our electric field intensity, so produced by this line charge given by this expression. So whereas y cap 321.4 minus z cap 76.2 kilovolt per meter. Alright, so that's all for now. Thank you, good luck, and have a nice day.